I'm Charlie Torrey from Physics, and before I introduce the speaker, let me remind you how we do things here. There will be about 45 minutes of a spellbinding presentation, and then please keep your seats after that, and we'll have about 10 minutes or so of question and answer. Then you're free to either follow up with the speaker or go on out into the building where there's all kinds of exhibits and demos and things that are there just for you to explore. In fact, I saw something about exploding pumpkins. So this is going to be very cool. Okay, let me tell you about our speaker. We have Dr. Sydney Chamberlin coming to us from Pennsylvania State University. That's where she is now, but she got her start here in Utah. Oh, heck. What high school did you go to? Bingham High School. I just asked her this earlier. She went to Bingham High School. Then she came up here to USU. She majored in math and physics. And she was a great example of a student who took advantage of just about every opportunity for a science student at USU. She tried everything. Not just things at USU either, now that I remember. But she did all kinds of research, won all kinds of accolades. I won't embarrass you by reciting them. But then she went on to get her PhD at University of Wisconsin in gravitational physics, focusing on the now very famous gravitational wave detection effort, which you've no doubt heard about and probably will hear more about. After getting her PhD, she went to where she is now, Penn State. She does some teaching there, some outreach, and some research. I'll let her tell you the rest, so please welcome Dr. Sydney Chamberlin.
All right, can everybody hear me okay? Okay, that sounds good. Well, it's really exciting to be back on this beautiful campus, which I really miss. It's a really nice campus. And I actually think it's pretty funny that we're in this room doing this, because this is the classroom where I took my first college physics class. And that was the class where I decided that I wanted to be a physicist. So it feels very funny to me that now I'm standing down here talking about physics to all of you. So that's kind of funny. As Charlie said, I'm at Penn State University right now. And the science I do is actually part of science through a really big collaboration. I work with over 1,000 scientists in a collaboration called LIGO. And LIGO stands for Laser Interferometer Gravitational Wave Observatory. So we're a bunch of scientists. We have this L-shaped observatories that you see in these two pictures here. And what we try to do with these L-shaped things is we try to detect something called gravitational waves. And it's a particularly exciting time in my field because we actually were in the news just a couple months ago. I don't know how many people heard about this, but we actually detected these things called gravitational waves. So this little screenshot here was actually from CNN's homepage back in February when we announced this phenomenal discovery. And I know the theme of this series is science in the movies, but this is so new, it's not even in the movies yet. The closest thing I could find for film is that Sheldon on The Big Bang Theory put this on his shirt. So I think that makes us really official. Okay, so let me tell you what I'm going to tell you about. I'm pretty excited about gravitational waves, so I'm going to try to tell you what they are. And then for most of the talk, what we're going to do is we're going to talk about the exotic, bizarre, weird astrophysical objects that produce these gravitational waves. And hopefully along the way, I'm going to try to tell you some of the mysteries about these objects and the things that we're hoping to uncover with gravitational wave astronomy, so that at the end you kind of have some sense of, so what, why should I care? And along the way, I've tried to incorporate clips from movies to go along with this theme. And I just have to say, there are so many really, really good science fiction movies and like epically bad ones out there that are both equally fun to watch. And there are far more than I had time to fit into this talk. So if you want some great recommendations on both good and bad sci-fi movies, come see me after, we'll talk about it. But ultimately, we're going to talk about gravitational waves. And that means we got to talk about gravity. So it all started with this guy. Here's my first clip.
Oh.
Yes?
You're Albert Einstein.
Thank you.
Wow. May I say what a great fan I am of yours?
Thank you.
That thing you wrote about light being bent by gravitation and the whole relativity thing, man, that is jiving. I'm still trying to figure it out.
Me too.
And as we all know, he's a very smart guy. And he started to think about this problem of gravity and how gravity works. And so here's what he came up with. And this is kind of abstract, so bear with me here. We like to think about the universe as being constructed of something we call space-time, which is a cool word, but the way we think about it is if you imagine a big sheet of spandex that's stretched really, really tight, and you take something heavy like a bowling ball and you plunk it into the middle of this spandex, then what it does is it makes a little dip, right? It curves that spandex. And that's the way we think about gravity right now from Einstein. We think that massive objects curve space-time, kind of like in this little GIF here, and then objects like the moon orbiting the Earth, well, they just orbit because they're following that curve on space-time. So massive things curve space-time, just like a bowling ball would curve a spandex sheet. And the more massive something is, the more it curves space-time. So it's kind of bizarre. And I'm going to try to explain Einstein's relativity. And this is extremely bizarre. Like what I'm going to tell you in the next couple sentences, you're going to think I'm just a crazy person saying crazy stuff. This sounds really, really weird. But bear with me. This is, for whatever reason, we think this is how nature works. So the first bizarre idea that Einstein put out for his theory is the following, that the rate at which time passes for an object depends on how fast it is moving relative to who's watching. And that's kind of a big sentence, so let's take a moment here and break that down. What this means is that let's say you and I are both wearing identical wristwatches. Okay? We have perfectly identical watches. They tick at the exact same rate. They are synchronized to have the same time. And you decide to sit in this auditorium. Well, I go and jog around campus really, really fast. We'll pretend I'm a fast runner, so I'm jogging really fast. And what this statement means is that when I come back into the auditorium after I've been running, our clocks aren't going to agree anymore. Time is actually going to have ticked at a different rate on my clock than on yours. Another example, got a little picture to help us out. If we had a rocket ship or maybe a really fast airplane, and we did the same thing, we took two perfectly synchronized watches and we stuck them one on our wrist on the ground and one on this airplane that's traveling really, really fast. The weird thing is that this airplane that's traveling fast, time is actually going to tick at a different rate for that plane because it's moving fast. And this is something that completely disagrees with all your everyday intuition, right? This isn't something you typically see every day, but it's actually a real effect. And the effect gets bigger the faster you're going. So of course, when I go run around campus, I'm not moving very fast. But there's lots of objects in the universe that do move really fast, and so this becomes important. Now that's the first idea. Here's the second one. It's equally weird. So the rate at which time passes depends on nearby pulls from gravity. So let me explain that a little bit. We know that gravity is the thing that pulls us down. And on the last slide, I said that gravity is the curvature of space-time. So let's have a little picture to help us out here. Here's a little picture that shows us how space-time might be curved for the Earth. So we have kind of our little space-time sort of spandexy looking sheet, and Earth is making this little dip down here. Well, it turns out if you go up higher, right here where space-time isn't curved quite as much, where you're further away from the surface of the Earth, gravity pulls on you a little bit less. Same thing if you're on the top of a tall mountain. Gravity would pull on you a little bit less than if you're down at sea level. And it turns out that when you're up that high, when you're in an area where space-time's not as curved, where gravity isn't pulling you quite as strongly, your watch ticks at a different rate than a watch for someone on the Earth. And so this sounds like just completely crazy stuff that you never deal with in your everyday life. But I'm about to tell you, you actually probably use this like on a weekly basis. Who's got one of these things? Anybody? Okay, so I see a lot of these things. Have you ever used GPS to go anywhere? All right, so in this case, you've used Einstein's relativity. So the way that your GPS works is you've got some satellites, and they're orbiting around the Earth. And those satellites are moving really fast. They're moving like 20,000 miles an hour. So this first effect thing here, this first really weird statement, the satellite is kind of doing this airplane thing. Its clock is ticking a little bit slower than yours because it's moving fast. And then secondly, the satellite is way up here. It's really high above the Earth. And space-time isn't as curved that high above the Earth. So the clocks on those satellites are ticking at ever so slightly different rates from your clocks. And even though it's small, if people who made GPS didn't account for that factor, GPS wouldn't work at all. So it's kind of fun to know that every day you're using Einstein's relativity, even though it's this completely bizarre and strange sounding thing. Okay, here's another film clip. This is a movie, Interstellar, that came out about 2 years ago. And it's kind of a short clip, so let me just explain what's happening. And I'm sorry as a spoiler if you haven't seen it. So we've got a couple astronauts. They're on a spaceship. And they want to visit a planet that they call Miller's Planet. And Miller's Planet is located near something called a black hole. And we'll talk more about those later. But a black hole is something that has a really strong pull for gravity, a lot stronger than the Earth. And so they're going to talk about this funny relativity thing that we just discussed. And it's pretty cool.
Still looks good. She's coming up there.
Hopefully you can hear. It's kind of quiet.
Planet is much closer
I love that. They're all bummed, and he's just like, well, that's relativity. Sorry, guys. So every year they spend there is 7 years on Earth, and that's relativity for you. Okay, but of course I work on this thing called gravitational waves. So I want to explain this a little bit. I talked a little bit about how we have this sort of spandex analogy for space-time. Massive things bend space-time. And a lot of the time people will do demos like this. They'll take a big sheet of spandex and stretch it over a ring, and you can put like a ball bearing in it, and it'll bend the spandex just like space-time would get bent. Well, it turns out if you take a couple of masses and you have them go around around each other, sort of orbiting each other, they make these little ripples that propagate outward. So this is how we think about gravitational waves. Massive things are bending space-time, and then when those massive things are moving around in space-time, they make ripples or waves. And I've got a slightly more scientifically correct version here, but it's the same concept. You've got a couple of massive objects out there. It could be anything. I'm a massive object, so if I start running circles around this chair, we're going to start making ripples like that. Okay? You make them all the time at your house too, so you can't laugh at me for it. Okay. So since you're getting hit by gravitational waves right now from the distant parts of the universe, you probably want to know how they affect matter, what happens if you get hit by a gravitational wave. And so what they are is they're these tiny little ripples, and they propagate outward. They actually travel at the speed of light away from the things that produce them. And then when they hit matter, they stretch it and squeeze it. So if you imagine holding a hula hoop, and this black circle is your hula hoop here, and the gravitational wave is coming straight out of the screen towards you, then what the gravitational wave does to this hula hoop is to like stretch it up one way and squeeze it down the other way. And let's get a different picture of that. Any Office fans in here? I know I've got at least one. Okay, so here's Dwight. Dwight's my favorite. And if Dwight's originally this height, then when he gets hit head-on by the gravitational wave, first he gets stretched up and he's like skinnier and taller, and then he gets shorter and wider. And then it just keeps going like that. So that's what's happening to Dwight when he gets hit by the gravitational wave. He probably has some really great comment to make about it. Now, of course, gravity is actually a pretty weak force. And we know this because in our everyday life, we can do stuff like pick up objects, or you can take a refrigerator magnet and defy the entire field of the gravitational field of the Earth just by picking the paper clip up off the floor with that magnet. So gravity's pretty weak. And these tiny ripples that are being made are really, really small. And actually, if we took the most strong, powerful gravitational wave that could be emitted in the universe, and we expose Dwight to that wave, the effect is still tiny. So for the strongest gravitational waves you can imagine, his height is really only being changed in these pictures by fractions of a proton. So I've really made it extreme in this picture, but it's not this extreme in real life. It's a very, very, very tiny effect. And I'm someone who works in a collaboration that tries to detect these tiny, 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 tiny changes that are smaller than fractions of protons, so changes in length that are that small. And so what I'm interested in looking for, and what people in LIGO are interested in, are the very most violent events in the universe and things that occur from what we call compact objects. So let me tell you what I mean by the word compact object. This is kind of fun. Okay, everyone was wondering what I was doing carrying this around, and I felt like a crazy person. But I have this piece of bread. Okay, this is just a roll from Smith's, right? And it has some atoms that make it up, and we could put it on a kitchen scale, and we could weigh it. It would have some number, like maybe it's 20 grams or something like that, right? And it occupies this little volume of space. And now what I can do, I was hoping this will work. This is actually really satisfying. Okay, I can squish it. And at the end, it's still the same bread. It's still got the same atoms in it. If we put it on our kitchen scale, it has the same weight, same mass as before. But now it occupies a smaller region of space, right? And so that's what this picture up here shows us too. If you take something like a star, and that star is bending space-time, maybe it bends it like this, but if you take that star and you crunch it into a smaller region of space like the bread, you get to a point where even though the amount of mass, the amount of matter is the same, because you've scrunched it into a small spot, it bends space-time in a much, much more extreme way. It's really, really quite wild. And so when you're doing gravitational wave astronomy, the objects that produce gravitational waves that we can try to detect are objects that bend space-time in this sort of extreme way that you see in this picture here. And it turns out that in our universe, the most interesting compact objects we know about are various kinds of dead stars. I like to call them zombie stars, and especially around Halloween, because it's, why should we be all serious all the time? It's more fun this way. So the most interesting astrophysical sources of gravitational waves that experiments like LIGO is detecting come from various types of dead stars in binary systems, and supernova explosions. And what I want to do now is I want to tell you a little bit more about these objects. And in going through this story, we kind of have to decide what we mean by the word dead star. What does it mean for a star to be dead, or even alive for that matter? So let's talk about the life of a star. So here's another film clip. This is a movie I really enjoy, WALL-E. I don't know if you guys have seen it. And it's a little bit of a long clip, but the cool thing to think about as you watch this is that every object you see in this film clip is made of star stuff. I don't know if you've ever heard this phrase, you're made of star stuff. It's true. And so WALL-E goes through this beautiful journey, and at the end, he'll get us started on how stars form. The only thing is there shouldn't be sound. No sound in space, so just pretend. Okay, so lots of really cool looking stuff in there. And at the end of this clip, he comes up upon this big purple cloud thing. And it turns out that this purple cloud thing, in the movie it's hiding a spaceship, but in the real universe what these big clouds are is something called nebula. And basically a nebula is just a collection of a bunch of atoms, some really basic atoms, dust, gas. And what happens is that all the little bits of dust and atoms and things, they're attracted to each other because of gravity. Gravity is an attractive force, makes everything want to come together. And so all these little bits of dust and everything, they come together and they kind of form little balls. And when those balls come together, they get hot. And there's a process that starts that allows a star to be born and to start shining. So I'm going to show this chart a couple of times tonight to show us how stars evolve over their lifetime. And it turns out that the evolutionary track of a star depends on how big it is when it's born. So we're going to start by talking about small stars, and by small I mean stars like our sun. So the sun that we have every day, even though it's big to us, it's actually a pretty small star on the scale of the universe. So the star is born in this nebula. Sometimes they'll call it a stellar cloud, but it's the same thing, just this ball of gas. And let's talk about how stars shine. So who's seen this before? Everyone's seen a periodic table. Good. So this is atoms, right? All the elements that we know of in the universe. And a lot of the stuff that's sitting in a star when it forms are hydrogen atoms. They're the simplest atoms in the universe. And if you find a hydrogen on the periodic table, it's here over on the edge because it's the smallest, it's the simplest atom. And so what the star does is it takes these hydrogen atoms and it sticks two hydrogen atoms together in a process called fusion. And it turns out when you fuse two hydrogen atoms together, what you get out of that is a helium atom. Helium is this element over here. And then you get a little bit of energy left over. It's kind of like if someone gave you $20 to run a lemonade stand, but it only cost you $14 to buy the stuff, and you've got extra money. And that's how it is for the star. It's got extra energy left over, and that extra energy is emitted in the form of light. So all that light that's coming out of our sun is because the star is fusing hydrogen together, sticking hydrogen atoms together, getting a helium atom and some energy for free. And so that's how it goes. So while the star shines, there's kind of this epic battle that's raging on the whole time the star is living. Because gravity wants everything in the star to compress. It wants to collapse under gravity. But then the shining of the light from the fusing of hydrogen atoms actually creates kind of an outward pressure. And that outward pressure balances the inward collapse from gravity. So as long as the star can fuse atoms together, it can stay shining. It can beat that inward pull from gravity. But, of course, nothing comes for free, right? And we've all had that point where your tank's running on empty. So every star out there has a limited amount of hydrogen atoms that it can fuse together. And eventually it's going to get to a point where it starts to run low. It starts to get low on hydrogen atoms. And when that happens, the really interesting stuff happens. The star actually swells up in size, it becomes bigger, and it forms something called a red giant. And it starts to look for something else it can fuse together, because if it doesn't have some elements to fuse together to produce energy to make light, then gravity is going to win in that epic battle from our last slide and collapse it. And so the star, what it does is it starts to fuse helium together. It's got plenty of helium atoms. So it's fused some hydrogen, it got some helium, and now it's got the helium, and it's got to try to fuse helium together. So the star will keep on shining by fusing helium atoms together. And when you fuse helium atoms together, what you get is a carbon atom, again with a little bit of leftover energy that can shine as light from the star. So that's how that works. But eventually, you're still going to run out of helium. There's just not an infinite amount of anything anywhere. And so when that happens, the star has reached the end of its life, okay? And what happens is that it basically sheds off extra layers of dust and gas. It's kind of like a big cosmic burp of dust and gas. And those gases form this thing called a planetary nebula, which goes and sits around the core of the star. And then what's left in the center is this object called a white dwarf. And a white dwarf is something we could call compact, if you remember the bread thing. It's compact. And if we drew it, what it looked like in space-time, so the sun curves space-time a little bit because it's massive. The white dwarf is more compact, like my bread there, so it curves space-time a little bit more extremely. And these objects, white dwarfs are actually not particularly interesting for LIGO. They're actually not compact enough to make really strong gravitational waves, but they're still cool, so I thought I'd toss this in here and tell you a little bit about them. They're pretty neat. This little graphic shows you the size of the sun compared to the Earth, okay? So the Earth, let's see if I get this pointed right. The Earth is this little tiny, tiny dot here, okay? So the Earth's quite a lot smaller than the sun. Well, white dwarf, you've taken everything in the sun and you've squished it into the size of the Earth, which is pretty crazy. And if you were to sit on the surface of a white dwarf and try to scoop up a spoonful of that stuff, it would weigh 15 tons. And to give you a feeling of what 15 tons feel like, my husband and I, we have a Subaru Crosstrek. It weighs about 1.5 tons. So 15 tons would be equivalent to holding 10 of our Subarus on a teaspoon. And that's like pretty heavy, right? I mean, bend your teaspoon. It wouldn't go very well. Now, white dwarfs they're actually really beautiful objects. And so these are actually both images from the Hubble Space Telescope. On the left, we have something called the Cat's Eye Nebula. And on the right, I can't remember, I think it's called the Helix Nebula. And if you look at the center here, this little white thing is the white dwarf that's left over. And almost all of the stars in our own galaxy, the Milky Way galaxy, almost every star we have is going to turn into one of these things. So it's a beautiful end fate of a star. But now we were talking about small stars, and if you remember, I said heavier stars do something a little bit different. So stars like our sun can't fuse carbon together, and they die and they become a white dwarf. Turns out if you have a really, really big star, something like 10 times the mass of our sun, it's so hot that it can actually fuse heavier elements together. And it turns out what happens is when a really, really massive star runs out of hydrogen to fuse, and then it runs out of helium to fuse, it'll start fusing carbon atoms together. And what you get from that is some oxygen, and then it'll fuse those together, and it'll kind of just keep progressing on elements on the periodic table that it can fuse together. And it kind of forms this onion-like structure, and you have these different shells that have formed from fusing different atoms together. But what happens is eventually it hits iron. And iron is a really interesting element on the periodic table. It turns out you don't get extra energy left over if you try to stick two iron atoms together. You actually lose energy. It's like they told you to go run the lemonade stand and they give you $20, but it's $30 for the supplies and you have to put it on a credit card. So it doesn't work, and the star says, I can't do it. And what happens when a star can't shine anymore is that it collapses due to gravity. And what happens for a massive star, so now we're on this lower track here with our big stars, what happens when the big stars run out of fuel is they undergo something called a supernova explosion. And it's pretty amazing. So here's a photo of another Hubble Space Telescope photo. This is a supernova remnant. So this is what's left over after a supernova that occurred a long time ago. And supernovae are pretty wild. So someone just said right before this talk started that there were going to be exploding pumpkins after this talk. And I have to tell you, although that sounds cool, it's not quite as epic as a supernova explosion, okay? A lot cooler. So basically these explosions release all these dust and gases, and they're traveling at ridiculous speeds. okay, really fast. And these things become so bright that for a day or two, they can outshine an entire galaxy of stars. An entire galaxy. Just one little star explodes and it outshines everything. It's wild. And there's a lot of mysteries. Okay, I just said, we don't really know how these things work. There's all this complicated stuff that goes on when the star runs out of fuel and it's got to collapse, and there's a lot we don't understand, but this is the kind of thing we can start to probe with gravitational wave astronomy. Now, after the supernova, this is kind of fun. I don't know if you can see this, there's a little blue dot sitting in the middle here. Well, this is something that has just been born from a supernova. So if we go back to our evolutionary path here, okay, for massive stars, when they have a supernova explosion, there are two possible outcomes at the end of the explosion. And the first one is an object called a neutron star. And if we look at how a neutron star curves space-time over on the right-hand side here, you can see it curves space-time a lot more extremely than the white dwarf. So the white dwarf, it pulled space-time down a little bit, but the neutron star is really getting extreme. And these are really interesting objects. So let's talk a little bit about these things. If you thought the white dwarf was crazy, wait till you hear this. This is going to knock your socks off, I hope. So you take something the size of the sun, and now you squish it to fit inside a city. So I tried to make a little picture to show you what one might look like over Salt Lake City. And now if you try to scoop up a teaspoon of this thing, it weighs 4 billion tons, which is a lot. And I decided also it'd be kind of fun for you to see if a neutron star suddenly appeared in Cache Valley. This is true to scale, the size of the neutron star. And so I don't know if you can really read this is Google Maps, but Logan's here, Providence is here, Smithfield is here. So this thing, is anyone here a runner, by the way? I was going to ask this. Anyone run like a 10K? Can anyone tell me how many miles 10K is? 6.2. Okay, that's the radius of this thing. So it's only about 12 miles across. So you're taking the mass of the sun and you've squashed it into like a 20K distance. Okay, it's less than a marathon probably. So that's crazy. And there's even more bizarreness to follow, but I'm going to show you another film clip first. This is a fabulous movie, and I'm just going to play the trailer, and we'll talk about it.
Radio source from deep space can neither be confirmed nor denied.
Whatever it is, it ain't local.
Position?
I checked interferometry somewhere in Lyra, I think.
Vega?
Can't be. Only 26 light years away.
I want all these people out of here. Your having sent this announcement all over the world may well constitute a breach of national security.
This isn't a person-to-person call. This may be an announcement to get our attention.
The president's called an emergency meeting.
You know those interlaced frames that we thought were noise? This has structure.
I'm going to recommend to the president that we militarize this project immediately.
There's no reason to believe that their intentions are hostile.
There's no proof of that.
Why don't they just speak English?
Mathematics is the only truly universal language, Senator. Buried within the message itself is the key to decoding it.
Those look like engineering schematics, almost like blueprints.
It is our belief that the message contains instructions for building some kind of machine.
A machine?
It might turn out to be some kind of a transport.
Transport? The fact is, you don't know what it does. It could be anything.
Nobody's saying this isn't dangerous.
They're gonna build it.
Who gets to go, though?
It's complicated, Ellie.
Who gets to go?
By doing this, you're willing to risk your life. You're willing to give your life and die for this. Why?
Very dramatic end right there. Okay, so this is kind of a fun movie, and what I want to talk about is what on earth was Jodie Foster doing? She's sitting on the hood of her car in the middle of nowhere with some headphones on, and there's this big dish thing behind her, and it looks pretty weird. So let's talk about what she was doing. What she was doing involves light. And in physics, we talk a lot about light because light's a pretty cool thing. It turns out that light doesn't just occur in the visible sort of way that we can see it. So right here, this is called the light spectrum. And in physics, we often like to say that light is a wave. And so wave, you can see this little red wave at the top. This is showing you sort of how long a wave would be for different types of light. Has anyone ever broken a bone, had an x-ray? A couple people? So if you've gone and you got an x-ray is a type of light that your eye can't see. And if you look at this little red squiggly wave up here, it's pretty short. It's really squished. We'd say it has a short wavelength. But there's other types of light. There's obviously the visible light that we're using to see each other right now. And if we look at the red wave above that, we've stretched it out a little bit. It has a longer wavelength. Then there's infrared light. If we go and we stretch that wave out, make it a little bit longer, that's what you could use with like military night goggles and stuff like that. And then down at sort of this low range here, if we stretch the wave out, make the length of that wave a little bit longer, we actually get radio. So even though when you hear the word radio, you tend to think of like sitting in your car and hearing with your ears. But radio is actually a type of light. And your car is able to convert that light into a sound that you hear. So what Jodie Foster is doing with this big dish thing behind her and this headphones on is she's listening to something called a radio telescope. And it's a telescope that can see this kind of light. So to relate to that story, here's someone who's kind of like Jodie Foster. This is a woman named Jocelyn Bell, and this picture was taken back in the 1960s. She was a graduate student at the time in the UK, and she's standing in front of a radio telescope, that big old dish thing behind her. And this is kind of a really fun story, and it's actually not too different from that movie clip we just watched. She and her advisor were listening to space with this big radio telescope, and they heard this thing, and it sounded like this. Okay, so they heard that crazy knocking, and they thought, whoa, that is so regular, right? It's very precise. And they thought, there's no way that something in nature could do it. It could be little green men, and they're trying to talk to us. And so initially, they actually dubbed this signal Little Green Men 1 because they didn't know what it was. And of course, they were really realistic about it. I mean, they didn't really think it was aliens. It was more of a fun idea, but they really weren't sure what it was. And it turned out that this weird noise they heard in the radio telescope was one of those neutron stars we were just looking at a couple slides ago, that neutron star sitting over Cache Valley. It turns out some neutron stars actually emit beams of radio waves out of them. And when they do that, we call them pulsars, but it's really just a neutron star emitting beams of radio waves. Now I want to explain how the radio telescope actually tries to hear a pulsar, but I need a volunteer. Yes. Okay, what's your name?
Ray, R-A-Y.
Ray. All right, so Ray is going to be a pulsar tonight, and all of you are going to be radio telescopes. So imagine yourself feeling very dish-like. And here's what I want you to do. Okay, I need to hold one of these in each arm, and I want you to hold them kind of up at like a weird angle like this, like one arm up, one arm down. Perfect. Maybe like a little more. Perfect. And now come over here in the middle, and I want you to just start spinning around like this. Okay. So as Ray is spinning, if the light from his flashlight crosses in front of you, you just heard one of those knocking sounds that Jocelyn Bell heard. So we actually think about this. We call it a lighthouse effect. Let's give Ray a big hand. Thanks. So these things are sweeping around like lighthouse beacons, and if you're sitting at a radio telescope, you can hear them. And now, I'm going to stop with pulsars soon. I get really excited about these things because they're so weird. I have to tell you a couple more really weird things about them. As if it wasn't weird enough that you've taken the sun, you squished it into 12 miles, and it's emitting beams of radio waves. These things are also spinning really fast. They're spinning as fast as your kitchen blender, 40,000 rotations per minute. So if you decided you want to land on one and hang out, well, you know, how long does it take for a day to go by? It takes, the Earth rotates in 24 hours. Well, one of these rotates 40,000 times per minute, so a day is like less than a second. You retire really fast, I guess. But you wouldn't really be able to enjoy it because the surface of these things is like 2 million degrees Fahrenheit. So you'd basically just be thermally obliterated upon landing. And then the gravitational pull of it is so strong, you couldn't even stand up. As soon as you got to the surface of it, you'd squish out like a human pancake and you'd just be flat. And you wouldn't be able to like lift your arms or anything. And then it gets even weirder. These things, they're actually not kind of like stars like our sun. You picture it as sort of a hot, bubbly thing. No, they actually have a hard crust on their exterior. And these stars, we think they undergo something called star quakes, which are actually like earthquakes on stars. So we think, we're not sure, that the inside of neutron stars is maybe full of some kind of weird liquid of particles, and the outside's a crust. And when a star quake happens, that crust can actually crack. And then another thing that can happen is these stars can actually get mountains that form on them, mountains on a star. But because gravity is so strong, those mountains can only be about 1 centimeter high. So they really wouldn't be very much fun to climb, and also you wouldn't be able to lift your leg to climb it anyways because of gravity, so I don't recommend traveling to one. But I will tell you, there's a lot of mysteries about them. We don't know, I'm going to call it how squishy they are, but we don't really understand matter at this kind of extreme compact density. It's like we can squish bread and understand it, but you can't actually produce this kind of matter in any lab on the Earth. It's too dense. We can't actually do it. So we don't understand how that matter behaves. We don't know if there are actually mountains on them, and we certainly don't really know what's happening in the middle of them, whether it's some kind of a liquid or something else. And all of these are questions that we can probe with gravitational wave astronomy. So that's pretty cool. Okay, so I talked to you guys about pulsars. They're really cool. But now we got to get to the second outcome of a supernova. I said there were 2 possible outcomes. And the second one is an object called a black hole, which I feel like everyone's always heard this in science fiction, but they're sort of elusive. So a black hole, if we looked at how a black hole curves space-time, we get this picture. And you can see the artist hasn't even drawn the bottom on because we just don't even know what happens at the bottom. We call it a singularity. But these things are really crazy. Let me tell you a few things that they're not. They are not responsible for your lost socks in the laundry. Everyone blames them. It's not true. Okay? They're not cosmic vacuum cleaners that are going to come and slurp up the solar system and we're all going to be destroyed. They're not gateways to places you don't want to go. And certainly they are nothing that you should ever feel worried about. Okay? The chances of you encountering one of these things is nil. It's never going to happen. Way more likely to win the lottery. So don't worry about it. What they are is something that's so massive that even light can't escape. And let's talk about what that means, to escape. If I wanted to escape the gravitational pull of the Earth, I mean, what would I do? I could try to jump. It doesn't really work. I just come back down. Or I could try to launch myself up. In order to get away from the gravitational pull of the Earth, I have to jump really, really fast, like a rocket. For rockets to escape the pull of the Earth, we have to launch them at speeds that are like 20,000 miles per hour. We call that the escape velocity. It's how fast you have to go to get away from that gravitational pull. And it turns out for a black hole, the escape velocity is so high that even if you were able to travel at the speed of light, which is what we think the fastest anything in the universe can go is, you still couldn't get out. Well, it's that massive, that dense. You can't get out of it. Now, everyone always wants to know what happens if you fall in. And, of course, what happens in the center of a black hole is a complete mystery. We don't know. But I can tell you with some certainty what would sort of happen to you if you were to fall in. So if the black hole were sort of the edge of this countertop here, and I started to fall in feet first, okay, so my feet are going in the black hole first, what's going to happen is that my feet are closer to the center of the black hole than my head. And that means that my feet are actually getting a little bit stronger of a tug from gravity than my head. And so what that tends to do is it kind of stretches you out. And you get stretched, like this picture here. And there's actually a very scientific term that we use. It's very serious. It's called spaghettification. This is what happens to you. It's my favorite science word. It's fabulous. So you wouldn't enjoy the trip. Don't do it. Don't go into the black hole. But that's what would happen. A couple of mysteries that we can try to probe with gravitational wave astronomy and black holes. We don't know how many black holes there are. So the first detections of gravitational waves are helping us to understand how many of these things are out there and what is the population of them like. And then another thing we don't know is how often do these things merge. So now LIGO, the experiment that I work for, we've actually seen 2 different pairs of black holes merge together. And that information is starting to tell us things like how often these events can happen. Now there's one more type of gravitational wave source I want to tell you about, which is a binary star system. And a binary system just means you have 2 stars and they're orbiting around each other. And can anyone name this movie? Okay, everyone knows. Good. I mean, I would be appalled if you couldn't. So Luke here, he lives on a cool planet. His planet is in some kind of solar system around a binary. So there's 2 stars in his solar system. He gets to have 2 sunsets, which is really cool. But a binary system, these things are pretty neat. So this top diagram kind of shows you how it works. You've got your compact object over here. And this compact object could be either a white dwarf, which we talked about. It could be a neutron star, which we talked about. Or it could be a black hole. It could be any one of those 3. And then it's got a companion star, and the companion star could also be any one of those 3, but it could also just be a normal star just shining light like our sun. But what happens is that, these things could just be happily orbiting each other for a really long time. But as we know, when stars like our sun run out of hydrogen to fuse together and they got to start fusing helium to keep shining, they expand. They form that red giant. They actually get bigger. And what can happen is that gas and stuff can get too close to the edge of this compact star, and the gravity from it starts to pull, siphon matter off of its companion star. It literally starts to eat its companion star alive. Okay? It's a star world. I had to put a zombie graphic in here. Because really, it's crazy. They're eating each other. So that's what happens with binary systems. Okay, so I'm getting kind of close to the end here, and I want to wrap up and kind of give you a sense. I know I didn't talk at all about LIGO's detections, and I'm happy as I will talk your ear off if you come up afterwards about how LIGO works. But I want to kind of give you a sense of why this is so exciting and why this is important. And it has to do with these really exotic objects that we just sat and talked about. We've got black holes, we've got binary systems, we've got neutron stars. All of these are objects that we can't build on the Earth to study. We don't have the ability to travel to them to study them. And we're limited in how we can study them using any kind of telescope that currently exists. So right now, gravitational waves are a whole new way of looking at these things, and they may hold the key to understanding them in ways that we can't learn in any other way. This is actually a little clip that's produced by the LIGO collaboration after our first detection. So what we detected were two big black holes, and the black holes were in a binary system, and they basically ate each other. They could merge together, and they form a single black hole. And they were really big black holes. They were about 30 and 35 times the mass of the sun, respectively. And what this video shows you, this is actually produced with supercomputers. So the physics behind this is very accurate. And what it shows you is what you would see if you were floating around in space sort of near this event when it happened. And it's been slowed down so you can appreciate it, because when we detected the merging of these two black holes, it happened in less than a second. It was really fast. But this is what it would look like if you were hanging out somewhere in the universe by this. And you can see there's all kinds of weird effects with the light going on. That's because massive things bend space-time, and light has to follow the curves of space-time, so light's getting bent in all kinds of weird ways. And these things come together and they coalesce, and then they form a single black hole that ended up having 62 times the mass of the sun. So that's pretty cool. And I'm going to try to play what it sounded like, because gravitational waves don't actually make sounds, but they do occur. They have a frequency associated to them, and you can actually hear that frequency with your ear. So we can actually play what this sounded like, but I'm going to warn you, it's really quiet, so you got to listen for it. Okay, that was it. So basically, it sounded like a grapefruit hitting the floor, so not very exciting. But when we start to hear things like neutron stars falling together, they're going to make a much more satisfying and long chirp sound, which is really fun. So the whole point here is that everything we've ever learned about the universe has been from using some kind of light. We've used our eyes, and we've looked at the night sky. We've built X-ray telescopes, gamma-ray telescopes, infrared telescopes, all those things on that light curve that we were looking at. We built all kinds of telescopes to look at them. But those are all types of light. What we're doing with LIGO, we're using gravity. It's totally, totally different. And the really neat thing is, every time humans have looked at them, I'm going to skip this one, but every time humans have come up with a new way of observing our surroundings, we've uncovered all kinds of fabulous and interesting, unexpected things. And we have no reason to think that it's going to be any different for this. We're going to find all kinds of stuff that we don't know anything about yet. So this is the birth of a whole new era, and we're all at the start of it, and it's really exciting. So I'm going to stop here and go ahead and take questions.
You go ahead and call on people, but maybe repeat the question for the audience.
Okay. Any questions? Yeah.
So would a black hole, it bends space-time, so would something be able to orbit a black hole?
Okay, so the question is, a black hole's bending space-time, and as we know, it bends it really extremely. Could something orbit it? And the answer is yes. Definitely, it could orbit it.
The other thing is, since the sun bends space-time, a curve, it bends in, but all the planets are on a level plane. Why is that?
Okay, so the sun is curving space-time, but if we look out, all the planets occur on a level plane. This is actually a really good question. This is a really deep question. So it's kind of tricky. All these little pictures I've showed you of this, spandex kind of thing where your space-time is getting curved. The problem is it's kind of like a two-dimensional analogy, right? Space is all around us in 3 dimensions and not just in 2. So it's really hard to picture, but actually those planets are, I wish I had a marker, I would draw this on the board, but they are actually sitting in these little areas where space-time is being curved, and they're rolling around. Have you ever seen, they have these coin toys in the mall all of the time. It's kind of like a big funnel thing, and you can put like a quarter in it and roll around. Just like that. That's exactly how the planets are orbiting too. Oh, yeah, I guess there we go. So I have really visual, so I draw everything, and I'm a horrible artist, so I'm going to apologize in advance, but so basically, the sun is sitting down here, and all the planets, they're kind of rolling around. And I'm not very good at making this 3-dimensional, but it would kind of look something like that. I hope that helps a little bit. But that's a really great question. At the back, in the green.
field extend from the black hole?
Oh, how far does it extend? Well, gravity's kind of a funny thing. It extends pretty far, but in terms of the region, maybe a good way to answer this is how far away do you have to be safe? Is that kind of what along the same path? So black holes have this term. There's this term event horizon. It's also the name of a movie I was going to mention, but I didn't. And the way this works is you've got your black hole, and it's really curving space-time. The event horizon is like your point of no return. It's right here, we'll just say. And how big that event horizon is, it depends on how massive the star is. So the bigger the star is, the bigger this radius is where you're safe. So the answer is it depends. But for the most part, you're so far away from any black holes that there's no need to worry about being anywhere too close to one. I don't know if that helps. Yeah?
So how does LIGO work?
How does LIGO work? Can I nerd out? I have some extra slides and I didn't know if I'd have time. But you opened up the Pandora's box and now you're going to have to shut me up at some point. Okay, so LIGO is something called a laser interferometer. And a laser interferometer, I know it's a big word, but what that means is it's an L-shaped thing that's capable of measuring really small changes in length. And we know that gravitational waves, their effect on matter is really small, and we know that the effect is just stretch and squeeze it. So our interferometers are an L like this, and as the gravitational wave comes, what it's going to do, my arms are like the L, it's going to stretch one arm and make it longer while the other one gets shorter, and that's going to do the opposite thing. So it kind of does this weird thing. And the way it works is we start with a laser. And lasers are always cool, and they're always in science. This is one reason you should come be a scientist, okay? Lasers are fun. We start with a laser. It's about a 2-watt laser, which is pretty strong, and then it gets amplified up to 200 watts, which will burn through a wall or something, I don't know. And it hits this thing called a beam splitter, and what the beam splitter does is the beam splitter lets half of the light go up one arm and half of the light go out the other arm. And at the end of these two arms, we have these mirrors, here and here. So the laser light hits these mirrors, and it bounces back. It recombines at this beam splitter, and it comes down to this thing called a photodiode. And a photodiode is just something that measures light output. And so what happens is the gravitational wave comes and it hits, so we know it stretches and squeezes stuff. As these arms change length, the light that's bouncing back on this photodiode, it interferes. And you either get light on the photodiode or not. And it's because light's a wave. So if you take two waves that are we call this out of phase. So if the tall parts of the waves and then the short parts of the waves, if they kind of line up like this and you try to add these together, then you get just a flat line. Whereas if you take two waves where the top parts and the bottom parts are in line, we call this in phase. If we add these two waves together, we get a bigger wave. And so this is what happens with the laser light, that as the light goes down these arms, it bounces back, and if it ends up combining in a way where those waves cancel, you get no light. And in the other case, you do get light. And so what LIGO does is it looks for light on that photodiode. And then, of course, there's a whole layers of complications to how we actually do it. I actually have some pictures, too. It's actually kind of an older experiment, really. It was constructed in the early 90s, and we collected data for a while, didn't find anything, but didn't expect to find anything because it wasn't really sensitive enough. And then it got upgraded. They finished the upgrades in 2015. Now, these things are huge in scale. So the L-shaped arms, they're 4 kilometers long, which is about 2.5 miles. It's a great place to go test your 5K running time. They maintain this whole 2.5 miles. So this is actually a picture of the beam tube at the Hanford site. This whole 4 kilometers or 2.5 miles is kept at what's called ultra-high vacuum, which means that they've sucked all of the air and atoms and stuff out of it. It actually took them 40 days to suck all of the air and all the molecules out of these tubes. So that's pretty impressive right there. And then there's a whole bunch of really phenomenal engineering that goes into making the whole thing work. And I could go on and on for hours, so I'll just stop, I guess. But feel free to come up afterward and we'll just go over it. In the black.
So is there ever a point where a star will just disappear?
Is there a point where a star could disappear and nothing comes after it? I mean, in terms of just it's there 1 minute, gone another minute, I don't think so. Although it would be possible if it went into a black hole, it wouldn't be coming back. So if it got eaten by a black hole, but anything that's kind of there, I mean, sort of just like I'm here now, and certainly I'm not just going to go disappearing. So same thing for a star. But if I got close to a black hole, I'd fall in and disappear. And if another star got too close, it could get pulled apart and fall in and disappear. In the yellow. So if the black hole's eating all this stuff, where does the stuff that goes in come out? We don't know. We have no idea. I have no idea. What happens is it goes in and it never comes out. And so the way the black hole works is there's no way to find out what happens inside, because how is it that we learn how things work? Well, we study them. We send in probes, like we could try to send in a temperature probe or a video camera, right? But once they go in, they can't come back out. And since even light can't escape this thing, I can't even try to like bounce a laser signal in there and see if that comes out. It won't come out. So there's no way for us to know what happens inside. But what does happen as these black holes consume other matter is that they get more massive. So they get bigger. So black holes can actually grow over time, and who knows, if the universe we think is currently expanding and expanding at an accelerating rate, so everything's moving away from everything else, but if it slowed down long enough and one black hole just started to consume everything, maybe it would become big enough to consume it all. But I don't think that will happen. I don't want to scare anyone. It's going to be okay. In the orange.
What's your position on, I've heard people talk about white holes. What's your position on white holes that might spit matter back?
So the question is, what's my position on white holes? And I have to confess, I'm pretty ill-informed about this whole thing, but there's some people who kind of tried to postulate what happens at the inside of a black hole. And if I've got this right, then what some people think might happen is that it's like a gateway to a different universe or to a different dimension. I just don't know. I really don't have a particular position on the whole thing. What I do think happens is that when matter goes in, we know that gravity pulls everything together. It compresses it more and more. So I think personally, this is just my opinion, this is not scientific, but what I think happens is that stuff just gets squished and squished and squished until it becomes atoms, and then those get squished, and then I have no idea what happens beyond that either, and no one knows. It's actually really cool that no one knows, right? That we live in a time where there's all this phenomenal stuff and no one knows the answer, but maybe we will.
If it got squished enough, would it be possible for the black hole to swing it out in a hole we can see to form something that would just spit it all back out?
Is it possible for the black hole to spit it back out? Not in this universe, I don't think. So could there be some other dimension or portal or something in there? Maybe. I personally don't think so, but maybe there could be. I don't know much about this stuff. What I can tell you is nothing that's crossed this event horizon and gone down in can ever come back out in our universe. In the back, I see some hands. Let's see, up here in the what was that? Oh, how come the black holes go together? So black holes, they have this really strong gravitational pull. Actually, everything in the universe that's got mass attracts everything else in the universe that has mass. So like this poster and I, we're attracted to each other because of gravity. We've got mass. And the same thing is true for all kinds of things with mass. And black holes are like the most massive things we can think of in a lot of cases. And so they're attracted to each other, and that makes them want to come together. And what happens? So if we go back to this video of these two black holes coalescing, you might wonder, why is it that they actually get closer to each other and merge? Why don't they just kind of orbit around each other? Well, the answer is they're emitting gravitational waves, and nothing comes for free. When you emit gravitational waves, you lose energy. So as these stars emit gravitational waves, they lose energy, and that makes their orbit shrink. And then as their orbit shrinks, they actually start to spin around each other faster. It's the same reason if you've ever seen like an ice skater who's spinning around with their arms out, and then they pull their arms in, they spin around faster. Same thing here. So these two things lose energy, and then they fall together. Okay, over here.
Do we still model like the movement, or like in an example like a binary system, do we still model that movement of black holes using like Newtonian equations, or is that like, I'm curious, I've never thought about that really.
Okay, so the question is, when we model these things, do we ever use what we call Newtonian physics to do it, or do we have to use Einstein's theories? That's kind of what you're getting at, right? So I didn't talk at all. There was this guy named Isaac Newton back in the 17th century, and he came up with kind of the first theory of gravity. And Newtonian gravity, if you ever take an introductory physics class, that's what they're going to teach you about how gravity works. And it's phenomenal theory. It's ultimately not quite as correct as Einstein, but it's phenomenal. It's what got us to the moon with Apollo. Now, in terms of modeling a binary system, you can get pretty far with Newtonian physics. But for LIGO with gravitational waves, we like to be a little bit more precise, so we do use the Einstein equations, which are basically relativity to do that. So the answer is it kind of depends on what you want to do. If you need to do something as technical as measuring something that's changed its length by a fraction of a proton, you've got to be really careful, and you've got to use Einstein's formalism. But if you're doing something like maybe you just want to estimate some basic properties of a binary system, there's no reason you couldn't probe that a little bit with Newton's physics.
We thank our speaker again.